Good afternoon. Today we're here to give our presentation titled Towards Usable Science for Assessing Tourism Sustainability in the Eastern Caribbean, from polar region ice melting to sea level change to rainfall. Our team members consist of Elenius, Fabian, and Essa Tengang from the University of the West Indies, and Karen Chen and David Wang from the University of Maryland, Baltimore County. As we all know, tourism is the main driver of GDP in Eastern Caribbean countries, accounting for about 40% of the GDP. Sunshine and beaches are the currency of the blue economy. However, it is becoming increasingly obvious that climate change will have a profound impact on the thriving of the blue economy. For example, sea level change will cause coastal erosion and loss of beach area, while increased heavy rainfall will pose flooding risks. This slide gives high-level overview of how global warming might impact tourism activity at different timescales. Specifically, global warming will cause ice melting in polar regions and increase ocean temperatures, which both may lead to regional sea level changes in the medium or long term. Meanwhile, local climate system will impact the rainfall, which in short term has effect on tourism activity. For planning purposes, a holistic picture of the interconnected component is crucial to assess the effect of climate change to tourism activity and sustainability. The proposed solution is an integrated system of usable science that combines data-driven models to support prediction and planning for regional tourism industry at various timescales.
Science is advancing our understanding of the impact of melting ice in polar regions on regional sea level changes. This slide illustrates the regional impact from the ice melting in Greenland and the Antarctic, which are two major contributors to sea level change at coastal cities, such as Miami. In the future, with access to relevant data, we will be able to estimate sea level changes in the Eastern Caribbean region and the specific impacts this may have for the region. The newly established IHARP Institute, led by UMBC, will help us to gain more robust understanding of the ice dynamics in polar regions. With these new tools, we will be able to more accurately forecast the ice melting process and assess its future impact to sea level rise at both global and regional levels. Another cause of sea level rise is the expansion of oceans due to the rising ocean temperature, as shown in the plot on the left-hand side. On the right side, we demonstrate the increasing sea level changes during the last 30 years around the Eastern Caribbean regions. In a recent paper in Science, researchers have explored a machine learning model to predict medium-term sea level changes with ocean temperature data. As part of the solution, we plan to adapt the model to predict regional sea level changes in the Caribbean regions 1 to 3 years into the future using the ocean temperature data. This estimate will be combined with the effect of ice melting, ultimately to reach the overall long-term and medium-term impact to regional sea level changes. Those estimates can be used to support strategic planning for Eastern Caribbean countries.
So this now brings us to the research questions. We explored two research questions in our analysis. One is the grand causal discovery with climate variables and tourism activity among Eastern Caribbean regions. Second is the predictive model for rainfall and tourism activity. We utilized two data sources: the 30-year monthly climate variable from 6 countries and monthly tourism activity from 8 member states in the last 20 years. We performed Granger causal tests to understand the causal relationship among climate variables among 6 countries. As highlighted above, we noted that the climate systems are interconnected. For example, rainfall of country B is not only influenced by its own climate variables, but also influenced by those from other countries such as H, A1, F, and A2. This suggests that integrate data from multiple countries is beneficial. Additional Granger causality analysis shows that 1, tourism activities are influenced by the climate variables. Another insight is that tourism activities among countries are interconnected.
Now let's move to talk about modeling procedures for predicting monthly rainfall. And we formulate as a machine learning problem where we predict monthly rainfall 1 month, 2 months, and up to 24 months ahead. We extract multi-resolution features from all countries' climate data from the last 1 year, 2 year, and up to 5 years of data. And we use random forest to fit the model. And we used 80% of data in the past as training and the rest of the data as test. The overall rainfall prediction model shows that all countries other than country F and G consistently shows improvement over default mean model at various forecast horizon from 1 month up to 24 months. Here we compare the prediction and true value of monthly rainfall for a given country H. The result shows that that firstly, the model predicts general well in normal year. However, the model fails to predict anomalous events during these months with more than usual rainfall. This motivates us for future research to predict rare events with more relevant data and powerful model. With a similar setup, we now try to predict the monthly tourism activity using the climate data from all countries. The slide summarizes the overall tourism activity prediction by country and by forecast horizon. We noted that all countries consistently shows improvement over default mean model at various forecast horizon from 1 month up to 24 months. Antigua and Barbuda and St. Lucia are two countries with largest number of visitors, and they are the one with relative good performance. The slides compare the predicted and true value of monthly visits to two of the countries, Antigua and Barbuda and St. Lucia, 12 months ahead. The result shows that the model is able to capture seasonal pattern and predict well at non-peak months. However, it seems to underestimate during the peak months.
Now, this brings us to the summary of our finding. We envision that the proposed integrated system that combines data or model insights from multiple sources will help the decision makers in the Eastern Caribbean region to predict the future sea level change and rainfall patterns and quantify its impact on tourism activity. This system will turn cutting-edge research into usable science and exploit the various data sources from the region to build robust predictive models in sea level change and climate pattern change, and ultimately inform the strategic and operational level planning for the tourism and beyond. And that is the end of our presentation.